So for number 49, we have that x is the infinite expansion 0.99999 and so on. And for item A, they're asking us, do you think that x is less than 1 or x is equal to 1? Now, most people who have not studied calculus will say that x is less than 1. However, once you understand the concept of limits, we can let x get arbitrarily close to 1 as we want by adding as many decimal places as is necessary. So actually, using the limit definition, this is exactly 1. Maybe one of the non-calculus ways for us to show it is the idea that, well, 1/3, we say that 1/3 is equal to 0.33333 and so on. Most people have no trouble accepting this. So if we multiply both sides by 3, we're going to have 1/3 times 3 is 1 is equal to 0.333. So that's going to be 0.99999 and so on, right? So, I mean, this is the non-rigorous way to show it, but it's this idea that most people have no trouble accepting this, but they struggle with this one. So once we've dealt with item A, that we say that x is equal to 1, now we're going to show it using the idea of calculus of limits and of series. So they want us to sum a geometric series to find the value of x. So x is going to be 0.99999 and so on. And if we express this as an infinite sum, what can we say? Well, we can say that x is going to be 0.9 plus 0.09 and then plus 0.009 and then plus 0.0009 and so on, because if you add all of these, you're going to see that you do get 0.9999 repeating. So we are constantly adding these terms where with every additional term, it gets a power of 10 lesser. So we can see that the first term is just 9 times 10 to the minus 1, because we have one decimal place. The second term is 9 times 10 to the minus 2. We have 2 decimal places. And then the third term, we have 3 decimal places and a 9. So this would be 9 times 10 to the minus 3, and then 9 times 10 to the minus 4. So we can see that we're just repeatedly adding these terms where 10 is being raised to a negative power of the natural numbers, and then it's multiplying by the constant 9. So once we understand this, we're ready to say that x is therefore going to be the sum of 9 times 10 to the minus n, where n begins from 1 to infinity. Because if we put in 1 here, our first term is going to be 9 times 10 to the minus 1, which is 0.9, which is in fact the first term, right? And so we're almost ready to sum it up, but we don't want this power to be negative, this minus n. So we're just going to say that, okay, that's the same thing as going n is equal to 1 to infinity of 9 times 1 over 10 to the n, because if you have a minus, that's the same thing as turning it into a fraction. So once we have this, we have put it in the form of a geometric series, and we can see here that the ratio, so the thing that's being raised to the power of n, the ratio is 1/10, and 1/10, that absolute value is less than 1, so the sum here is convergent. We can calculate it. So we just have to remember the formula that whenever we're summing up an infinite series, I should put this as a times r to the power of n, and begins from n is equal to 1 to infinity, the value of this sum here is AR1. So the first term divided by 1, not AR1 rather, A sub 1, so the first term of this series, divided by 1 minus the ratio. So A sub 1 in this case, so when you plug in n is equal to 1, we've already seen that you get 9 divided by 10 to the power of 1. So A sub 1 is going to be 9 over 10. And then the ratio is going to be, the thing that's being raised to the power is 1 over 10 in this situation. So let's plug this into our summation formula. So on the numerator here, we have A sub 1, which is the first term, which is just 9 over 10. So we're going to have 9 over 10 divided by, that's going to be 1 minus the ratio, and the ratio in this case is 1/10, so 1 minus 1 over 10. And if we do this, we're going to have on top, that's going to be 9 over 10 divided by 1 minus 1/10 is just 9 over 10, which is in fact 1. So we could see that using calculus in an infinite series, that the sum is in fact, the value 0.999999 is in fact equal to 1. So that's it for item B. Now for item C, they ask us how many decimal representations does the number 1 have? And we just saw that 0.999 is a decimal representation for 1. It's exactly equal to 1, as we've just proved. So one of the decimal representations here is 0.9999999, and the other one is just 1.00000 and so on. So you might be asking yourself, okay, well, if we can approach 1 from the lower side, 0.999, why can't we approach 1 from the upper side, so 1.0000001? And the reason that we can't do this is because then the ratio would be, the absolute value would be greater than 1, and it would not be convergent. So we can find here 2 representations, and then it's asking us which numbers have more than 1 decimal representation. So the way that we got 2 representations was, well, the first one is just putting 0.000 after the end of the number, so that's not very interesting. But the second one, what was most important, is that we got this as a sum of a ratio, so it was a fraction 1 over 10 to the power of n. So for it to fit this bill here, it has to be a rational number. You have to be able to express it as a sum of infinite fractions, right? So we're going to say here that these are the rational numbers. And so that is it for problem number 49.